Okay, so it's 1 p.m., so we're back from the break. Welcome back, everyone. So first we have a talk about integrating AI and simulations. This will be Bethany, Lusch, Riccardo, Balin, and Somal Patel. So take it away, Bethany, whenever you're ready.
Thank you. So as Somal said in the Slack, if you have a chance to grab an interactive node now, that would be helpful so that when we get to his demo, you're all ready and not waiting in the queue. So first I want to say a little about why you might want to couple AI and simulations. For example, you might want to use machine learning to decide which simulation to launch, like you're doing active learning and you need to select simulations that will improve your machine learning model. We also see use cases where people are replacing part of a simulation with a machine learning model, maybe because that part is slow or that part is inaccurate. And you also could want to couple them in order to reduce I/O. For example, your simulations are too big to ever save to disk, and so you want to run the machine learning at the same time as the simulations are running and pass the data over without saving to disk in the meantime. And people also are using machine learning to control simulations, such as picking some parameter or numerical scheme. And I have more examples, including papers, in the repo, or if you go to the bonus slides in this deck. And broadly, there's a few different ways to couple simulations and AI. Loosely coupled would be that you are that the AI and the simulation are different processes. And tightly coupled would be, for example, the simulation is calling the AI and they block each other. And today we're going, in the first part of this session, Saumil will show you an example of tightly coupled, and in the later part you'll see loosely coupled with SmartSim. And extra loosely coupled would be that your simulation and AI aren't even on the same resource. For example, using Theta and Cerebrus, something like that. And as a little bit of background for the first demo, we're going to talk about a tight coupling between Python and C++. You can see more details in the README, but basically we're able to pass data back and forth between Python and C++ without copying it. And we can stay on the device the whole time, which someone will talk about more. But for example, you could stay on the GPU the whole time. And to do this, we use the Python and NumPy C APIs and using Akka. And an advantage of being able to integrate Python into your simulation would be being able to use convenient Python libraries like machine learning libraries that aren't easy to use in C++. So here we're like a diagram summarizing the demo. On the left, we have C++. We allocate an array, U, and we're looping over time solving a PDE. Each time we're updating that array. And we pass U over to the Python side by a pointer. So that's not a copy. But then on the Python side, we do copy it just to keep the history for a while, and that's in that data array. And then when the simulation's over, then we can do some analysis. The data, Python already has access to the data, so we can do some plotting in PCA. And this time we didn't show neural network training, but of course you could do that too. All right, that's all my slides. And Saumil, are you ready for the demo?
Yep. Can you hear me?
Yes. Thank you.
Okay, great. Okay. I'm going to share my screen. Let's see. Can you guys see my terminal?
No, it's loading. Yes, now I can.
Okay, great. Okay. So, all right. Hi, everyone. My name is Somal Patel. I'm a computational scientist at ALCF and the Computational Science Division. So I'm going to walk you through a tutorial that kind of prototypes or demonstrates this idea of coupling simulations with AI. And I'm going to do it kind of using, as Bethany mentioned, Theta GPU. So hopefully everyone who is going to participate has gotten an interactive GPU or an interactive node. And so just to kind of set up the lay of the land, this tutorial is going to solve, it's just going to solve a simple kind of 1D partial differential equation, the Burger's equation, for those of you familiar with PDEs. And there's going to be a kernel associated with solving this. And we're going to execute that kernel on the device. So just to kind of get things started, if you can see my screen, let's see, I'm on a Theta GPU node here, and I'm already in my, in the repo folder called Theta GPU _ Oka. There was a link provided to it on the Slack channel. If you need it again, please refer to the SDL discussions channel. But for now, I'm just going to talk about setting up the environment in this case. So if we just go to the script called set oka environment.sh, what I want to emphasize here is just make sure you have the right path to this particular directory on Theta GPU. So what you want to do is, I'm focusing here on the Oka cache directory. This is going to be important because in the application which uses Oka, and I'll talk a little bit more about what Oka is, but essentially it's going to compile some special files which will load binaries in a just-in-time manner to a specific directory. And that directory constantly gets referenced every time you run the application, so that you're not, every time you want to rerun it, you're not recompiling that same kernel. So just make sure you have that specified here. And then from there, what you want to do is, let's see, we just want to go ahead and build it. So, well, first you want to check the environment. So one way to do that is by doing this thing called Oka info. When you source that script I just mentioned, it's going to point to an executable, which then gets loaded into your path. And then you're able to run this executable and do the Oka info, which then spits out information about your CPU and CUDA. And this is a feature of the Oka library. It kind of gives you some low-level features of the hardware that you're running on. And so in this particular instance, we're seeing the interactive node. I'm getting 1 GPU, and it's showing the host processor that's available to it. So from here, in sourcing that script, you can also see the modules that are available. And in particular, we have CMake and the Conda module that's there. So that's going to be important for this. So next step is to do Conda activate. And then we have Conda, I already activated that. And then we just go ahead and build. Let me see that everything's fine and everything's building. And if people are having trouble, I can certainly help you kind of offline or in the breakout rooms later. but I just wanted to kind of demonstrate that how to build this thing. So from here, we then go into the install directory. Sorry, and then we run the kernel with the executable that's there. It's called burger. And then you should see a whole bunch of output kind of going to standard out, showing the expected calls to Python, kind of also showing the time step information. And then in this particular example, we're going to be collecting data to do a singular value decomposition. So, and then we use matplotlib to spit that data out. And so you should see two images, two PNG files, which they're pictures. I mean, you'll have to kind of download them to your local desktop through maybe Globus or something, but they should be similar to the repo link and the images provided therein. So that's kind of how building this thing and seeing the output is going to work. What I want to do is get in the last few minutes, I just want to go into some of the key features here. So like I said, this application uses Oka, and Oka is a performance portable abstraction layer that allows you to run using different backends. So you can use CUDA if you're running on CUDA hardware. You can use SYCL for Intel hardware, HIP for AMD, and right now, in this example, there's a couple of ways to kind of use Oka, and in particular, I want to point you to this way to instantiate the device. And so that's a way for the application to kind of recognize that there is a separate GPU device on the hardware that you're running on. And so this is kind of like the Oka API syntax that can be used there. In addition to that, you can set memory. And so there's a way to instantiate memory there using the following syntax here. So let me set number here. You can see in lines kind of 80 to 90. This is critical kind of Oka API hardware that'll get you going to use the proper backend. And then for another important part of this is kind of exposing the backend pointer to some of these memory that we're setting and then using and running on. So that's enabled through creating this backend pointer, also enabled through the Oka API. And then there's also the kernel that is saved in a directory called kernel. Here I'm calling it burger.okl. And that, as you look at it, it kind of looks, it's written in a C-style API, but it looks very reminiscent of like a CUDA kernel that might be running on the device. And so when we're using the Python C API, we can pass this information to our own Python function, which I'm calling here pyit. And you can find information about this object kind of further up in this particular code. But I do, just in the interest of time, kind of get to the point of why we're doing this at all. And the idea is that we want to be able to use the memory on the device where it is without transferring it to host, and then kind of using traditionally the Python module NumPy kind of libraries, which are traditionally done on the host. instead of incurring that cost between device to host, we can do it directly on the device. So and the way we actually do that is through this CuPy framework, where under the ND array object, we can specify certain parameters that are informed by a low-level CUDA API within CuPy, where we can point to memory that's resident on the device from the C function, or from our main.cpp file that we set. And from there, we can grab that memory and start storing it in the CuPy arrays in order to do the analysis that we care about. So so yeah, that's kind of like the point of what we're trying to do in this case. And this is all to say that, you know, we are able to do things in situ on the GPU, and this is just one demonstration. So I'm going to stop here and let my colleagues continue. But if you do have any more questions, I'm happy to continue the discussion on Slack. And so what I'll do is stop here and see you on Slack. Thank you.
All right, I can take it from here. I'll share my screen. If you can see it.
Yep, we can see the GitHub page.
Okay, great, thank you. Hi everyone, I'm a postdoc at ALCF, and I work on coupling simulations and machine learning. And so today I'm going to give a little tutorial on how we can do that using a tool called SmartSim. So to go over the material, I'm actually going to use the README file in the workshop repo. So that's where I am right now. And if I go into coupling simulation and machine learning, and then we have this README file, and then we follow the third bullet point, go to the link, and this takes us to the README file for SmartSim. So I'll start with a little introduction of what is SmartSim, and then move on to how do we deploy workflows, and then a tutorial, and actually we get to run a few examples. So SmartSim is an open source tool that's developed by HPE, and this was designed to facilitate exactly what we're trying to do, that is combine simulation or traditional HPC with machine learning workflows. There's really two key components to SmartSim. One is what they call an infrastructure library. And this is a set of APIs that allow you to basically manage your workflow. So you'll get a driver Python program, and that allows you to start and stop your jobs. This could be the simulation or machine learning applications. And this part also interfaces with the scheduler. So that's how you can launch jobs. For example, on Polaris, we would use PBS. And on Theta and Theta GPU, we would use Cobalt. And then part of the APIs is also the ability to deploy an in-memory database, which they call the orchestrator. But what this is, and we'll see a few examples of it further down the README, is a clustered or sharded database that allows you to store any data that you'll need for machine learning. So this could be training data or inference data in memory throughout the duration of your job. So this avoids writing any training data or even metadata that you might need to share between simulation and machine learning to disk. And you can all store it in memory in the database. The other component is what they call a Smart Redis client library. And this is a set of APIs that allows basically your applications to connect to the orchestrator. And they provide APIs in the 4 more common languages: Fortran, C, C++, and Python. So this means that you can build workflows with any application, and more importantly, any existing application. You don't have to change the language of your application to be able to build workflows. And these client APIs allow you to transfer data to and from your applications in the database, but also you can act on data that is stored within the database. So you can, for example, load JTraced, Python, and machine learning runtimes, and then you can evaluate these. So you can do some pre-processing on your data, or even evaluate models for inference. There's a few interesting links here if you want to learn more. There's a good documentation, the source code, and they also have a zoo of examples, so you can see how to build up a few different types of workflows. But for the purposes of this tutorial here, I wanted to talk about two main things, and that's how do we do in situ training or inference. Another word for in situ that we're using here is online. So how do we do online training? Well, there's an example, sort of a sketch of the diagram right here. And what we do is we set up three different sort of components. We have a simulation, we have the SmartSim orchestrator, which is our database. And then we would have what's sometimes called the data consumer. This could be, for example, our distributed training, if we're trying to train something. You can see sort of the data flow would be from the simulation into the orchestrator, and then the distributed training would then go grab that data. And as I mentioned, you can store the training data within the orchestrator for the entire duration of the job. So that means that your distributed training program can keep accessing that data or whatever new data your simulation is adding to the database throughout the entire duration. And one thing to note is that this approach allows you to basically do fully decoupled coupling, I would say, between simulation and machine learning. That is, the machine learning does not block the simulation. The two components do not block each other, and they run also on separate resources. This could be both CPUs and GPUs, but basically your machine learning and simulation are not interfering with each other. And then the other approach is to do online inference. In this case, we really just need the simulation and the orchestrator, because as I mentioned, we can load models and then perform inference within the orchestrator. And that's exactly what we do. One thing to note is that the backend for the SmartSim orchestrator is compatible with TensorFlow, TensorFlow Lite, Torch, and Onyx runtime. So that means that really you can load a model that you trained with any of these machine learning frameworks. And then it allows you to not have to switch between different frameworks, different libraries that you use to do the training. Another thing to note is that the orchestrator supports both CPU and GPU. So you can do inference and you can evaluate these models that you've loaded within the orchestrator on both CPU and GPU resources. So you can access the accelerated inference times you would get by running on the GPU there. One thing to note about this workflow, though, in this case, we call this loosely coupled because simulation and the orchestrator are separate resources. But in this case, they do block each other. The simulation has to send the data, which is a blocking operation, evaluate the model, which is also a blocking operation, and then get the data back. So the simulation is paused while you're performing inference. I also wanted to mention that there's two ways we can deploy these workflows. One of them is called clustered, the other one co-located. Clustered means that each of these three components, for example, for training, runs on distinct resources. So this means the same machine, but for example, different sets of nodes within that machine, which means that now communication between simulation and database, for example, must happen between different nodes. There's some pros and cons of this approach. The main con is that data transfer, as you might imagine, is not as efficient, but this really allows us to get very creative with our workflows because all of the training data or inference data, basically all the data that is shared between simulation and machine learning is available within the same database. The other approach is co-located, and you can imagine reproducing these diagrams on each node. So now the simulation, orchestrator, and distributed training share the resources on each node that you run your job on. So now communication is only within the node, but this means that we need to deploy one database on each node. And each database contains a fraction of the total amount of training or inference data. And so while communication here is the most efficient, if you're trying to access data that is perhaps not on your database, on your node, then that task is not trivial, but it's doable. And to showcase some of the differences in performance, I want to show this plot right here. Here we have the time it takes to communicate inference data from the simulation to the database for the co-located approach in blue, and for then the clustered approach with a few different sizes of the database, 1 node and 4 node. So not only is there a big difference in just the communication time itself, we can see that for the co-located approach, because we're actually not communicating between nodes, just within the node, the cost is fixed as we increase the number of nodes. So this approach, the co-located approach, is very scalable. To run with SmartSim, you require to install a few packages. And so to do that, I've created a Conda environment that is available for everyone to load. And you can see how that is loaded right here. You would just first load the baseline Conda module, and then you would go activate the specific Conda environment that I've built for this workshop. You can also build it yourself and then or clone the one that I've provided for you, and then add different packages that you would like on top of it. But it does contain sort of the essentials that will allow most people to run their machine learning workflows. Okay, so for this tutorial, I've designed a little training and inference set of problems. And I've designed these examples to use both Python only, and then one case uses a Fortran simulation type of code. So this would give you a flavor of how do you add sort of the smart Redis clients and build sort of linking the right libraries for a code that is written, for example, in Fortran or C++. And what we're doing here is really just learning a model for this simple polynomial that you see right here, this x squared plus 3x plus 1 in the domain from 0 to 10. So you can go to the specific example by clicking this link here, clustered Fortran example, and we'll go there in a second. But I wanted to give a quick overview of what is actually happening. We'll see that first, we'll basically just be executing the driver script that I mentioned earlier. And this driver script will first launch a clustered database. In this first example, we'll use the clustered workflow. And this will get 3 nodes. The first node will run the database. The second node will run the simulation, or the Fortran reproducers for a simulation, which will basically do a loop over time steps, and every time step send new training data to the database. And lastly, we'll launch a distributed training program on the third node. This uses PyTorch and Horovod to do distributed data parallel distributed training on the GPU. And this is what actually learns the model. And we'll be able to see the output of what is going on with the load data and train model.out files. And then this will save the model _JIT file. So that's where the model is contained. So moving over to my terminal, that's actually where I am. I am in, basically I followed that link. So that brought me to Polaris, Fortran, and then train CLDB, which stands for co-located database. So what we'll do is we'll actually just, as the README says, just submit this, this submit job. And in just a few seconds here, we'll see the job launches. Here we're submitting to the SDL workshop queue, which is quite open. So we should see this just taking a few seconds exactly to start running. And what we can do is we can tail a few files. The first file we'll tail is this one called train_CLDB. This will give us a status of basically the driver and what the driver is doing. And we see here that in the output, it's printing. We says that we're running on 3 total nodes. These are the node IDs that we got. And then it's actually splitting those 3 nodes for the 3 applications. So we have node 1 is running the database, 2 is simulation, and 3 is machine learning. So what we can do now is we can go, okay, we can tail a few more files here. Okay, so here I'm tailing the files basically that give you the output of the simulation and the training model. So on the top left here, you're seeing basically this loop over time steps where we're seeing that we've initialized all the Smart Redis clients, all the clients were initialized, we sent some metadata to the database, and now we just have a loop over time steps in which we're sending training data with a specific key to the database. Now here on the right, we're now seeing that all components are now running, and soon in the bottom left, we'll see that the output for the distributed training program will fill in exactly. So we're using Horovod. Here we have 4 ranks, 1 rank for each GPU that is on a Polaris node. And so here it's saying we've initialized all the clients, retrieved the metadata that was sent to the database. And in just a few seconds, we'll see now that we're starting a loop over epoch, in which, as you can see here, we're going to grab, and I printed this output specifically to show what the machine learning program is doing. And each rank of the machine learning is going to grab one of those tensors that was one of those basically arrays of training data that was sent by each rank of the simulation. And they're splitting them equally. If you go through these, you'll see that the tensors are split into 4 distinct sets. And then each rank of the machine learning is then doing mini batch stochastic gradient descent to then train a model. We've reached the loss tolerance that I said just for this little example. That means that we are now done. You can see, in fact, here on the right, both programs completed and then the job exited. And this gave us this model.jit.pt file. That's actually our model. So I see that we're out of time. I had just a little inference example that would just take 1 or 2 minutes to run. So I can stop here, but I believe is there a break or is there another talk right now?
There's another talk, but I'm the one giving a talk, and it should be fine. I think I have a 30-minute slot, but a 20-minute talk. So feel free to do like the one more example.
Okay, yeah, thank you very much. So basically what we do is we go back 1 directory. Here there's another example, which is inference underscore CodeDB. This is basically the next step, which is now we've trained a model with this first example that I ran. Now we basically copy this model to the inference directory. And now what happens when we, if we want to do inference, that is run a simulation, and we want the simulation to make predictions from this model. And these predictions would then be used to, in a real case example, integrate, for example, the Navier-Stokes equations or any PDE that you might need. So here, we can do the same thing. We just submit the submit script that is in this specific directory. Now I'll also go to that same location on my other terminal. We wait just a few seconds for the job to load onto the machine. Okay. Okay. So this is a co-locate approach. And so in this case, we actually only had to grab 2 nodes because, well, that's how many nodes I specified. Just show you the output. This side, we have 2 nodes, but here now on each node, we have the simulation running on the CPU, the database running on the CPU, and then the simulation is sending data to its database, the database that is on its node. And then inference is actually being performed on the GPUs of that particular node as well. So here on the left, soon you'll see we've initialized all of our clients. We've uploaded the model. This is that JIT traced file that I mentioned earlier to the database. And you see we have 16 simulation ranks per node. So this means that rank 0 on node 1 sent the model to its database, and then rank 16 on node 2 sent its basically the same copy of the model to its database. And now we're just going to do 5 loops of this example, a simple for loop. This would be sort of a loop over time step. And we'll see that each rank is sending inference data. And here we'll have sort of a little output saying finished sending inference data. We're then evaluating the model, and then we're retrieving those predictions back. We just did 5 time steps for this little example. So you see here, this is done. And what we get out is, just for the purposes of plotting, 2 files. Basically, we get a file with the predictions and also the true data on node 1 and node 2. And I have that already plotted, so we can see it right away. And so what you can see is actually the way that I set it up to demonstrate how the 2 nodes are doing inference on different data is I actually split the domain. So node 1 was doing inference only on data from 0 to 5, or x equals 0 to 5, and then node 2 from 5 to 10. You can see, of course, the model is not very accurate. That's just because I set the tolerance pretty high just to make the training quick. But you can see that we are able to follow that polynomial shape pretty well. And so, of course, then you would expand this and do work on a physics problem, and that's exactly sort of this type of workflow is what we apply in my group to do turbulence modeling for computational fluid dynamics. And I can stop right here. Thanks for letting me go a little bit over time.
Awesome.
If you,
yeah. Oh, sorry, go on. Yeah.
Oh, I was just gonna say, if you have any questions, also please send messages on Slack, and then also I'll be available at the end of the day during the breakout rooms to go over these examples again and go into the code further.
Awesome. Thanks a lot, Riccardo,
Thank you.
Bethany, and Saumil.